last time we were talking about categories. So today we're going to talk more about categories, but we're going to see how we can use them and talk about functors. So let's maybe just have a very quick recap. So we had this definition of a category, which was given by a set of objects. And so maybe, do you want to do this on the board while I, do we have a pen?
I have a pen.
Good. So it's given by a set of objects, and then for any two objects, we get a set of arrows between the objects, right? The morphisms. So, and then we said that there has to be an identity morphism from A to A for every A, and we must be able to compose morphisms. So if you can go from A to B and from B to C, then you can go directly from A to C. So the way we visualize this is we draw some dots for the objects and we draw some arrows for the morphisms, right? And then we sometimes label them because they're all given by different things. And what Conrad has drawn in red is the identity on that thing up there. There's an identity for everything, so we don't normally draw it. And there's a compensation for everything, so we don't normally draw it, but it must exist.
So what I'm saying is whenever the black things exist, the red things also exist. But exactly, the red things are the things we don't normally draw in because the rules say they must exist. Right? I'm drawing them in here to tell you what the rules are. Yeah.
Then we saw some, yeah, sorry.
I was going to say, there's another thing that happens when we draw diagrams like this, where so the zero-dimensional things are the objects and the one-dimensional things are the morphisms, and the two-dimensional spaces enclosed by the one-dimensional things are equations. So what I'm saying here is that the path from here to there by following F to here and then G is equal to the composite FG, because the paths start and end in the same place. So that's in a diagram like this. When there is more than one way to get from A to B, you're claiming that it's the same way. So that's how you state an equation as a picture. You draw a diagram where there's more than one path between 2 points.
Because then it makes sense to ask if the paths
are the same. So you're saying when there's more than one way between 2 points is it doesn't matter which of these ways you choose. Same thing.
Okay, and then we had some examples of categories. So the one that's important to remember, or the one you're very familiar with, is the category of sets, where the objects are sets and the morphisms are functions.
One thing that's really noticeable is that, one can play this game, and people do, with Haskell types and functions, but Haskell functions sometimes go wrong in horrible ways. And so in fact, it's slightly dishonest to say that Haskell types and functions form a category. They nearly do, but they don't. Whereas Agda's totality promise means there ain't no lying. We're telling the truth that sets and functions form a category.
But, and then we saw some examples. And today, let's talk about functors. So these are the functions that are the right notions for categories, right? The morphisms that are the right notions for categories.
Yeah. Oh, we did mention that every, or did you just fill that stuff in?
I filled that stuff in. So if you, we teased about this in the lecture, and if you want to go and have a look at it, you can. But it's not so important.
Right. Well, something's good about it, though. I mean, the point is that we wrote down a definition of what it was to be a category, and then we separately wrote down what the definition was to be a monoid. And it turned out we didn't need to do that, because it ended up that a monoid is nothing other than a one-object category.
Right. And that's what this is saying, half of that, right? It's saying if you have a monoid, you get a one-object category. See, we have exactly one object here. But you can also go the other way if you want. So they are really the same, right?
And likewise, the pre-orders are exactly the categories where there's no information in the morphisms other than their existence.
Right, just the fact that one thing is less than another.
Right.
yes, you're saying we have you give me a pre-order, I give you a category, where the objects are given by the elements of the pre-order, right, the carrier of the pre-order. Okay, so, but now let's talk about functors. So you might remember this from Haskell, right? Where there is such a thing as a type class of functors. And the thing you do with functors all the time is you have some kind of containery thing, right? Which is called f of functor. And then you would like to apply a function to every element of the container, right? So saying that if you have a function from A to B, then you get the function from f of A to f of B. So it's a way of lifting the functors into the container, right? The functions into the container.
If you have buildings that are full of people who are alive, and you have a source of gamma radiation that can turn live people into dead people, then you can take your building full of live people and turn it into a building full of dead people without harming the building in any way.
That's of course being the simplest example of a function. So
that's my fault.
This is a special case of fmap where this function here is constant. Right? You notice this. Swap the A and the B's here.
Yeah.
So if this is a constant functor, then you can take a building full of anything and turn it into a building full of dead people. Right. Right. So this makes sense in Haskell, but it also makes sense much more generally. And Haskell did not invent this. It stole it from category theory. Right. That's where it's coming from. Because we noticed that this kind of looks like something that makes sense in the category of sets, right? It's talking about functions, Haskell functions. But we could also do this more generally, where we say, we just ask ourselves the question, what is the right notion of a mapping between categories, right? So I have two categories, and I want to say, what does it mean to transform one into the other? And then if you think about it, well, the first thing you should be able to do is you should be able to turn the objects into objects, right? Because we want to have a mapping. But then you should also be able to turn the morphisms into morphisms, right? So here's one category, right? Let's call it D, because I'm going to draw another one over here. I'm going to call C, which also has some dots in it. Okay, so to give a functor from this category to this one, I have to, okay, let me also draw some arrows. Okay, so I have some arrows, I have some compositions, I've drawn some of them out. I have some identities, I haven't drawn them all. And now to map from here to here, what do I need to do? Well, I should at least map all the dots here to the dots here, right? And I should map all the arrows here to arrows here. So let's see if I can do this. To map this one to this one, 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 and also this one to this one, right? So for every object here, I give an object here. And now I should map the arrows from here to here, but I should not do it in some random way, right? Saying that I take an arrow and give back another arrow. I would like to if arrows line up here, they should also line up here, right? So first of all, so if I'm this arrow, I have a limited choice what it makes sense to map it to for this to be nice, right? And because it started here and ended up here, that means that it should start here where I mapped over the so-called domain of the arrow, and it should end up here where I mapped the codomain of the arrow, right? So in this case, I have no choice. This is F, G, H. Then I have to say that this thing here is the functor applied to F, making a functor which I'm calling big F here. So this thing here, if this was A, then this is the functor applied to A. This thing here, we call this B, that to reply to B. And if since I have an arrow from A to B, I have to make a new arrow from f of A to f of B, right? So I think that makes intuitive sense, right? Do you agree?
Yeah. Let me put it a different way. You've seen like a diagrammatic map of, let's just say, the railways in Scotland. What makes it any good? I mean, the fact that Scotland has actual railway stations in it, joined up by actual railway lines. And what's useful is that there's a mapping from the dots on the railway map to the actual railway stations in Scotland. And every railway line drawn on the map corresponds to an actual railway line between the stations, between the rail stations, the R-E-A-L, R-A-I-L stations that are indicated by the dots on the map. Right. So that's to say, it's not just that dots are mapped to dots. It's that the whole picture represents something in the other space. Right. Every picture, every diagram in C turns into a diagram in D, because we're forcing the images of the lines, the images of the arrows to map up, to join up with the images of the dots. Yeah. So when you've got an equation that holds in C, and you send it across to D with a functor, the image equation will also hold.
Or
yes,
yeah.
Yes.
So like that's maybe the misunderstanding. So like if we had like A and B, then like let's say the one next to the right would be like C.
Yeah. Good.
So
good choice on name. Yeah.
Just to understand it further, so would the functor of that be going like F and G together, like similarly, or
Right. So now yes, I haven't. So okay. So I said that.
we took C and then A, so like A to C over there.
So I haven't said where I'm sent G yet, right? But actually, I have no choice by what I'm going to tell you next, because I also want to preserve the composition. Right? So since this red arrow here is the composition of F and G, then I need to be able to send it to somewhere such that if I compose it with F, I get this thing here. Right? So this has to be F of G, because then this thing here is F and then G, right? So then I have to choose where to send it. I can choose this, but that's the same as the composition, because I want, like always, I want my maps to be structure preserving, right? And composition is structure. So in the same way, I want to send the identity up here to the identity over here, right? So I'm sending identities to identities and compositions to compositions. And that's again a choice, but it's the only sane choice, right? Because if you don't do this, then you can't work with these things. They're just random maps again.
Right. And again, key thing to emphasize is that when you even draw a diagram like this, you're making a literal category on the board whose objects are the ink dots and whose morphisms are generated by the ink arrows. And to be able to say that this diagram is about something happening in some other category is to give a functor from the inky category to the thing that you're trying to talk about. And it's the fact that it's a functor that makes the diagram have any useful information content whatsoever. So you're saying, here's a picture of something that is realistic and that describes something that's happening somewhere else.
Okay, and I haven't quite specified the functor yet, right? So I said where all the dots go. I said where this and this morphisms go, they go here and here.
Yes.
I've implicitly said where all the identities go because they have to go to identities, right? I've implicitly said where all composites go because they have to go to composites. But I should also say where this H is going, right? So this has to be a morphism from the domain, the image of the domain of H, which is here, to the image of the codomain of H, which is here again. So again, I really have no choice here but to send this to the identity, right? Because that's the only map I have from here to here. Okay, so that's the picture, and maybe it looks, I mean, I hope it's intuitive that you're just trying to send things to the same things and preserve all the structure you have, right? That's the general idea.
Let's ground ourselves in some kind of concrete.
Yes, let's have a real example. So this is very much a toy example, right? You can tell because there's different colors. But so here are the trees that we defined in coursework 1. So they have leaves and they have binary subtrees with an X stored in the middle, right? So this is something which takes a set and returns a set, right? So we could ask the question, is this a functor? And that's very much a Haskell question.
Yes. I'm just joking that you can tell by the ASCII artwork that this was me who wrote this type.
Yes.
About 10 years ago.
Okay, so what do we have to do to provide a functor from set to set here? Look at the definition. We have to give an action on objects, and we have to give an fmap action on morphisms, right?
Yeah,
which is exactly
which joins up properly.
Yeah. So we take a morphism from X to Y, and we make a morphism in D from act of X to act of Y, right? And then we have to preserve identities and composition, like we said. So let's see if we can do it. So we have to give an action on objects. So this should be something that goes from set to set. Let me make that a bit bigger. Okay. And because I named this tree, I want to explore if this tree data constructor here could be made into a functor, right? So far, it just takes a set and gives you back a set. So I say, well, I want this to be my action on objects. And now to say that this extends to a functor means that I can also map it on morphisms, which in this case are functions because this is in the category of sets, right? So now this looks a lot like that Haskell thing we had, right? If you take f to be tree, so that if you have a function from X to Y, you get the function from tree of X to tree of Y, right?
You know, you expect anything that has a sort of vaguely containerish quality to it. You know, it's a thing that stores elements. If you have some operation on the elements, you should be able to sort of deploy that operation systematically to all the elements being stored. It very often happens that you get a goal to fill in one of these record structures, and you know you're going to have to write a recursive program, so you immediately break it out as an auxiliary function.
Yeah. So yeah, so that's you could, but you're going to suffer later because you need to prove things about this thing.
Yes.
And you can, but I mean the determination checker is then a little bit iffy sometimes because you're talking about the tree you are defining, right? So it's almost always better to just make a separate thing that you can talk about separately.
It's sometimes a bit too stupid when it comes to checking that, you know, records that refer to themselves, it's not bothering to check that it's later fields in the record that are referring to earlier fields in the record.
Yeah, it's not clever enough to kind of stratify the definition. So that's what we're doing by hand here,
yes,
right? By
basically
pulling this before.
Yes. So we're having our own quiet argument with the termination checker. What it boils down to is build all the pieces individually. Then once you've got them, pack them up.
Yeah.
You know, use these goals to tell you what to break out as separate tasks. So you don't coming up with this type wasn't an act of creativity because
right,
you know,
that was
goal one,
given to us from here, right?
You know?
But also often you actually want to use this function, right? You're
Yes.
not just defining a functor for the fun of it. So then it's not a bad idea to have it with a nice name rather than calling it fmap of tree, right? Okay, so how do we define this? Now we are back on familiar ground. So we have a function from X to Y. We have a tree of X and we want to make a tree of Y. And what can we do? Well, we have two choices. We could immediately give back a tree, or we can look at our input tree, right? So you could say, well, we could ask auto, and auto will say, let's just give back leaf.
Yes.
But that's not great, right? Because I mean that satisfies this constraint. It does give us a tree for every tree, but let's see if we can prove the identity law with this. It says that if f is the identity, then this function here should be the identity, right? But you give me t, I give you back a leaf is definitely not the identity. So the definition of a functor tells us that this is not a good function definition.
Yeah.
Right. Okay. So yeah. So if you make this a singleton type, then indeed that's also a functor. But so that's not good. So I think we should. Right. We can't just return t here, right? Because it doesn't type check. But we can look at t and see if it's a leaf or a branch. Okay. And if it is a leaf, well, then this identity thing is going to be satisfied, right? If we return leaf. And also, what else could we possibly do? We have no x, so we can't possibly make a branch, right? So here we're kind of forced to return the leaf. And here we have two subtrees, and we have some data, which is an x, and we have to make a y. And I mean, you could probably figure out what it is already, but if you want to think a little bit more generally, then often when you define a functor, it's a structure-preserving map, right? So we should here preserve the structure, which in this case means that if we are a branch, then we should return a branch, right?
Yes, we need to preserve everything about being a tree while destroying everything about being an X.
And
People should die.
Yeah.
yeah, right. So here we have our tree with live people, and now we're going to apply our gas function that,
It's,
or whatever it was, asbestos.
it was gamma radiation.
Gamma radiation, right?
It's,
Okay, so here we can do f of x, right? And okay, and one thing I want to say that what does this wishy-washy thing about structure preserving mean? Well, it means exactly that we can prove these laws eventually, right? If we do the wrong thing, then we won't be able to prove them. Okay. Pardon? I think it will go for leaf. No,
no, it went
Okay.
right.
it went right. Yeah, so it swapped the trees. That's also bad news for the identity law, right? We started with the left, and it said, okay, let's put the right recursive caller. So yeah, you can't really trust auto all the time.
Yeah.
Yeah, what
A
I told
fun
me.
thing to do is to start proving the
Right.
laws already.
Yeah, but yeah, so that's how you can trick auto into giving you the right thing, right? Because there's only going to be one thing that actually satisfies the laws. But you're going to have a hard time proving the laws if you don't have the function yet, though, right? Because you're doing it blind.
Yes. Well, you can fill in some things.
Yeah.
I mean, that's the marvelous thing, right? It will compute for as much information as you give it.
Okay, so now if I fully normalize this, okay, we see we have these implicit arguments here that have already been instantiated here, but otherwise it looks like the right thing, right? So that is my action on morphisms. And now I need to prove the identity. So I have to prove this. And then the first question we ask ourselves is, why is it stuck, right? And why is it stuck? Well, this thing on the right is not stuck. It's as easy as it can be. This thing on the left is stuck because we haven't applied it to a leaf or a branch yet, right? See that these equations only hold if you give it a leaf or a branch.
Yes, the tree hasn't turned up yet.
Yeah.
They get a reference.
Not well, we'll see. But so the next, so that's why it's stuck. And then how do we get it unstuck? Well, we are proving an equation between functions, right? So it's usually a good idea to use this function extensionality thing we annoyingly have to postulate. I usually call ext. I postulate it somewhere, I think in the categories file.
Yeah.
Right, extensionality. And
Right. This is a form of cheating that we are allowing you for this purpose.
yeah, and what does it say again? It says that if you have two functions, f and g, and you want to prove that the functions are equal, then it's enough to show that they are equal for every argument. So that's always a good move to do if you're trying to prove that two functions are equal.
Yes. So annoyingly, the built-in notion of equality in AGDA thinks functions are equal if they have the same implementation. So if you think of them as boxes that full of machinery, right? The equality is looking inside the boxes at the machinery. Whereas that's not the way we want to think about functions. We want to think about functions as things where we don't care what the machinery is. We just care what we can observe by shoving inputs in and seeing what comes out.
Okay, so here
We're allowing ourselves that view.
Why is that?
because it's easy to implement.
Because it's easy to implement.
Okay, so here now I have given for every input t, which is a tree, I now have to show that if I apply tree map with the identity function to t, I get t back. Right.
There's no way to have a t on the left. On the before the equals.
Right. No, there is not because
You need exception.
I need to apply this X principle. Yeah. Okay. So now you said, okay, is it enough to just give it a tree? We could try, right? And the answer is no, it's not. Because again, why is it stuck? Well, this thing is stuck because we don't know what the t is, right? We only have equations for when the t is a leaf or a branch. So we don't have an equation that talks about this for an arbitrary t. So we have to pattern match on the t, and in this case we are going to be, no, we're not. So this is what usually happens, right? You barge in, you realize you have to use extensionality, you get your t, and then you realize, oh, I have to pattern match. So what you normally do then is you take one step back, you look at the goal, you copy the goal, and you either put it up here tree map.
Yeah.
Okay, and then I realize this is talking about x, so we better introduce an x.
Is now a good time to demonstrate Control C, Control H?
Probably. So you can do this by hand, or you can just type in the name of the thing you want and do Control C, Control H for help. And it will give you the type signature of the helper function with that name that would fill the current goal, and it will try its best to quantify all the things you need. Right.
Yes. So you imagine that you're going to solve the problem by applying a function that you haven't got yet. And Control C, Control H says, well, if you want your fantasy solution to work, you'd better give your function this type.
This identity tree map, even if you got rid of the identity tree map.
Yes.
Yes. So I haven't loaded this file yet, so that doesn't exist.
Yes. So what we're saying is, oh, I wish there was a thing that did this, that went here, called identity tree map. What would I have to make for that to be sensible? And it comes up with this.
Yeah.
Just copy that.
Yep.
So just copy that. I think it's even in my green, I think, yes. So that's not the one I deleted, that's the one down here, and you can tell because annoyingly it didn't normalize this as much as you might want, right? So it's saying category ID set rather than just lambda x to x. But
Yes. The type it generates might not always be pretty. You might, it's a place to start from, and then you can think, okay,
right.
what do I actually want?
And in this particular case, it's actually annoying because it's not
tree
defined
hasn't been
yet.
defined yet, but that's fine because you can.
I can call it tree, or
Uh,
I could put it in a where clause here, I think.
Yeah, that works. Although,
But it's nicer to actually call it tree.
Yes. And to tree map. All those other things.
Right, this is tree map.
I
Yeah,
actually quite like category id set there, but
right.
okay.
Okay, so when you actually normalize it, you get the thing you wanted, right?
Now you get that.
So now I have t on the left hand side, so I can pattern match on it and see that in the leaf case, it's raffle. And I can't just say raffle here, right? Because I have to deal with the subtrees. So computed, the X is the same, but I need to see that, well, the left subtree and the right subtree are the same, right? So I can do a easiest way out is to do rewrites.
You do that through acquisitional reasoning,
Yeah.
Yeah.
It's one of those.
I mean, it's one of those things. If you're being impatient and you just want to get on with it, then it's easiest to just do it in a rewrite. Right. Okay. And the story here for preserving compositions is going to be very much the same, right? So we're trying to prove that too.
You do.
So, right, because again, these are not the same thing, right? This is a tree map of something. This is a function that composes tree maps. So if I just do Control-C, Control-H, it asks me what I want to call my function. Call it helper. It's this.
Yeah. Sometimes it gives you much more stuff than you actually want.
Yeah.
So I would get rid of
Right.
basically that the first line of that type.
Yeah, okay. So it's I can do that, but the type signature mentions the F and the G, right? So then I just have to make sure. So these were implicit here on the left. So I can do that. And it's the same. Okay. And the store is again the same. It's stuck because we don't know what the T is. Pattern match on the T. Here it's raffle. Now we should be good, right? Helper is of course not a great name for these things, but at some point you run out of good names as well.
It's not a bad name when it lives in a
In a
where
where
clause.
Yeah.
If you promoted it to the top level, then it would be a really bad name.
Yeah, something like that.
Yeah.
Or I usually call them lemma when they live in a where clause. But okay, so we've seen one example of a functor with something you could have written in Haskell, right? Because it goes from set to set and it deals with containery things. Yeah.
I'm guessing it's just that was a function point to itself, but the definition of homework that's just point to like some line instead. It's like I can see why they are the same. You just want to double check.
Yeah, sure. I think I would say they are the same because the tree map here is defined in this very particular way.
Yes, it's turning leaves into leaves and nodes into nodes.
And doing recursive calls on the subtree.
So,
Your proof is always going to do the same, follow the same structure. Right?
Yeah.
Yeah.
It's sort of the archetypal one step down structural operation that, where structural induction is always going to work. There will always be an induction hypothesis that does exactly the right thing corresponding to the recursive call, and you just go for it.
Yeah. Okay. So in Haskell, all functors are basically of this form, right? They take some data type, which is a functor from set to set, and it's a container thing or something, and then you can apply the gamma ray inside the container. But in category, so that's one very special form of functor. But we don't need to limit ourselves to this special form anymore. Now we can have functors between different categories, right? It doesn't have to be from set to set. or from C to C. These are called endofunctors because they stay in the same place. But here's a very simple example of a functor which is not from C to C. You mean a type class in the Haskell? Yeah, there is something similar. It's called instance arguments, but let's not go into that.
Let's not go there.
So here we are just giving concrete functors, right? By giving all the fields, and if we want to refer to it, we have to refer to a specific one. But so Connor, can you think of a functor from monoids to sets?
Let's see. Click. I can click.
Good.
Okay, well, to give it, I have to give its pieces. Split on the results. Okay. So what am I asked for here? I'm asked for something that extracts a set from a monoid. Is monoid open?
I think so, but let's see.
Because, well, what was in a monoid? There was a carrier set, and then there were some operations that did things. So I don't really have a lot of choice here. If the monoid has anything to do with it, I'd probably better pick out. Is it called carrier?
Yeah.
Right. Okay. So that's so we're basically what we're saying is take a monoid where we've got a carrier set and we know we've got some goodies, some extra structure that we like. And what, all we're going to do is forget that we have this structure.
So remember, a monoid was a set together with a way to squish things together and a unit thing.
Right. So someone is going to give me a monoid homomorphism and an element of the carrier of X. So what's going to happen, right? I need to produce an element of the underlying carrier of Y. And, well, what was a monoid homomorphism? It was a function from the carrier of the source monoid to the carrier of the target monoid that moreover respected all the structure we're forgetting. So scrub everything after the moreover, we're winning.
So we can, if you don't remember that, we can click here, right?
Yes.
See what the homomorphisms were. There were monomorphisms. We see it's a function that preserves some stuff.
Yeah. So I can at least get an excellent candidate for my
carrier of Y, yeah.
Functorial action. So let's go. Will this work? I get my function out of my H and apply it to my X. Okay, I'm actually going to golf that, so I think that's good. Right, so what we're saying is, just pick out the underlying carrier set and forget that it's got these operations. Just pick out the function between the carrier sets and forget that it preserves the structure. And then if you remember what we did for identity and composition for monoids was to say, well, actually the identity function will do fine because it preserves the structure, and actually ordinary function composition will do fine because it can't help but preserve the structure. Because so we're in hopefully fine form here in saying, is the actual function that we get the identity function? Sure is. Yes, yeah. That was control U, control U, control C, control comma. And once again here, we're saying, well, composition for monoid morphisms was composition of the underlying functions. So again, we are straightforwardly laughing. So this is basically saying there's a whole class of functors that correspond to taking stuff with extra structure and throwing away the extra structure.
And that's going to, almost by definition, preserve the remaining structure, right? So that's going to be a functor. Okay, so
what's
so you could, but I mean, all functors are covariant. It's just that.
Yes. Oh yeah. We should do that construction at some stage.
Right. Okay. So I don't think we have time to do this. So the thing I wanted to point out here was that that forgetting things is easy, but it's often quite boring, right? Which you can see that it was a very simple definition. So often the interesting functors are the ones that go the other way, where you start from, say, set, and you want to construct a monoid somehow from this set, right? Or here, another example, you start from a set, and you want to construct a pre-order. So this is where you actually have to have some creativity and make something up, right? And usually if you don't do this in a random way, you do that in some canonical, whatever canonical means way, then this is usually a functor, right? So here, I think I forgot to, I can pretend that I wanted to leave this filled in because we don't have any time, but the original plan was to fill it in. So what am I saying here? I'm saying that if you have a set, then there is a way to make a smallest order on this set, right? Where the carrier is the same as the set. I won't have to use the set somehow, right? And the order relation on this set is given by equality.
Yeah.
So the only way two things can be ordered is if they are actually the same. Right?
Yes. So reflexivity tells you that equality has to be part of it.
Yeah.
And what we're saying here is there's equality and nothing more than that.
So I'm forced to at least have this, and then I'm saying, okay, let's stop. And then it's easy to show that it's reflexive, right? That's by construction. And transitivity is exactly given by transitivity over quality. And the fact that there is nothing interesting is this other axiom we're assuming that all identity proofs are equal, uniqueness of identity proofs.
Yeah, so that's going to work. There is enough time for one thing which I think is important to say, which was that we said a monoid can be seen as a one-object category. And if you do that, if you've got two monoids seen as one-object categories, and you ask, what's a functor between those categories? What you'll see is that you have to provide exactly the data for a monoid morphism. And if you ask, once again, we said pre-order is a category with boring morphisms. So it's reasonable to ask, if you've got two categories that come from pre-orders, what's a functor between them? And guess what? The obligations to deliver a functor will turn out to be exactly that you deliver a monotone map. So what's funny is that when you take the concept and you figure out how to see it as a category, the notion of functor tells you the right notion of homomorphism.
So again, you can use this to kind of guide your intuitions to see what you should look at, right?
This is part of what we mean when we say kind of category theory is a kind of way of organizing your thoughts so that there are fewer concepts you need to engage with stuff.
Right, okay, so to finish off this example, and then I think we're done for this week and we can pick up next week. So we have taken a set X and we have defined a pre-order, right?
Yeah.
as a carrier in order, and then it satisfies these axioms we require of preorders. But that does not yet give us a functor, right? We also need an action on morphisms. So we have to take a morphism in set, that's a function from x to y, and now we have to give an order-preserving map between x with equality as the order to y with equality as the order, right? But that's not so hard. So what does it mean? It means that if x is equal to y, then f of x has to be equal to f of y, right? But everything preserves equality. So we can just use the same f, and we can use the fact that everything preserves equality to show that it's order preserving. Okay, and then again, it's easy to see that if we plug in the identity here, we get the identity out. And if we plug in a composition here, we get the composition out, right? So these are again very easy to prove. So it's one example of, I mean, you're trying to, so again, you have a forgetful thing going the other way, right? If you have an order, you can forget about the order and just get the set. Then it's often fruitful to ask, what could I possibly go the other way in some interesting way, right? And this is one way to do it, where I take the smallest possible thing. You could also think about, is there another way to do it where you try to make, so I'm trying to make as few things as possible related, right? You could also try to make as many things as possible related. And that's also going to work. It's sometimes called a chaotic order on the set.
Chaotic order. Yes.
Yeah. And you could ask, is that also going to be a functor? And spoiler alert, it is. Right. But I think that's a good time to stop, and we'll do composition next time and the category of categories.